thanks a lot for the organizer for having me. And glad to be here. I apologize, I have a little bit cold. I caught a flight here. So you have, it's not my normal voice. And so I'm going to talk about the TILT. So the short acronym for transforming random low-rank texture. So I have heard a lot of work today, about the theory and algorithms and about how to recover sparse and low-rank structures. And then there's a lot of development in recent years. So my talk, I'll try to focus more on application. So what cool stuff we can do with it, right? And hopefully that will in return will suggest some new problems that we may have not thought about, some new models, and become models. This is actually joint work with my former student John Wright and also colleagues at American Canvas, especially on the theoretical and algorithm side. I also John Chen Ling and Yasu Yuki Matsushita and so on. So I don't have to re-emphasize why we're interested in sparse and low-rank technique, because really these days we try to really make sense out of this massive high-dimensional data, right? So we try to really extract compact knowledge from such massive data. Why? Because our brain only processes a few bits per second. We need to have a very, very compact representation of what's in the data for us to make good decisions. So, and also, one assumption we relies on is that the data do have structures. If it's just random brawl, whatever we do, we lose, right? So there's nothing clever, intelligent you can do about it. So we have to make the assumption that the data do have good structures. And the intrinsic degree of freedoms are very compact, very low dimensional. Right? Hence, all the techniques going after. So this is actually, those assumptions are fundamental for us to do almost anything intelligent about this kind of data. Images, we try to compression, noise resolution. Videos, the reason we can encode them very efficiently because they're highly correlated. It has tremendous low dimensional structures, right? Web data, the reason we can index them very efficiently is precisely because there's collaborative information. Right? So I'm going to just focus on one source of redundancy. Right? So just using one example to give you an idea, right, of why this kind of technique is very fundamental and crucial for modeling data. One source of data we have a lot these days is image. Right? Each image actually is a big matrix. Right? So if you think about the entry, the pixel is just the entry of a matrix. Right? So it could be a huge matrix, especially now the camera gets more and more higher resolution. Each camera, even iPhone 8 megapixels. Okay? So you're dealing with huge matrix essentially. But good thing is that if you look at those kind of images, they're very, very representative, right? You know that they're actually very regular. I don't want to define what regular means, but when you saw them, you know. There's a good structure in them, right? And there's, and also, if you treat them as a matrix, you can imagine they're also highly correlated, right? For example, this bilateral symmetry. There's one column on the left and it's going to be exactly the same on the right, approximately. Right? So the question is, there's a lot of those regularities and the symmetries, and how can we actually harness them for all kinds of purposes? We'll see, all the different things. So how we really learn those dimensional structures, for example, those textures, right? They're highly periodic and regular from high-dimensional data. So the problem is not so easy, right? In computer vision, so far we are talking about all these idealistic algorithm models that we can try to recover low-rank matrix with a little bit of noise or sparse errors, but in computer vision, especially if you're practitioners, you're dealing with problem like this. You're given data like this, right? You do not control, because you don't control the data acquisition process. You're presenting the data to you. You have to deal with there's a missing or corruption, occlusions in front of the data. There's something very regular behind it. Right? And how do you handle those corruptions of this data? And also, furthermore, you don't get to see the frontal view. Very often, there's a deformation. So suppose you apply a PCA to this kind of data, you can imagine what you would get. You very much get garbage. Right? If you try to force yourself to do a low-rank approximation, you can argue that you are not really getting the fundamental structure you are looking for. So I'll go very briefly. Then the question is that we decompose this into two steps. First, of course, how do we handle corruptions? Suppose there's some low-rank structure in the data, but there's some corruption. How do I handle it? And also, one more step. What if there's also additional transformation in the data? how can we handle it, right? So this part is actually related to many people have talked about today. It's called Robust PCA. I'll go very, very quickly, an overview of what we do, but I'll try to focus on this part and also its applications. So give you a lot of room to think about for future applications. So this is traditional PCA, try to estimate low rank matrix despite ID Gaussian noise or bounded dense errors. So everybody knows how to do it, single value composition. So the problem, as I said, very often you get this kind of problem. You try to decompose, the error is not a noise. There can be gross corruptions, right? So actually could be some low dimension structure plus some scratches. You still try to impede those scratches. Can you recover this? Right? And then this error model is no longer Gaussian anymore. Laplacian or sparse. You can make your own assumptions. The question is, how do you decompose the data matrix into a low rank plus sparse components? Right? Do this automatically. Right? This is actually you can say think about this as sort of like robust PCA. Right? Traditional PCA handles small noise. This actually handles gross errors, outliers. Right? There's actually a tremendous effort to try to solve this problem in almost every literature, every area. This is some representative ones in computer vision. Almost every community has its own problem. So it turns out, there's actually one way to make this problem plausible is actually you have to assume some incoherence between the low rank part and the sparse part. Under fairly broad conditions, turns out actually indeed you can actually do it. But the optimization problem is not trivial. Right? We know that rank minimization and minimizing sparsity of the signal are both actually NP-hard problems. They're very, very intractable. Right? The lesson we learned from computer sensing is that actually we can actually, instead of solving this hard problem, we actually relax them with convex circuit and try to solve them instead. Right? Everybody can do this. This actually becomes a polynomial time algorithm. And the question is when they're actually equivalent. Right? There's actually a lot of talk today about just like, for example, solving on 1, then you actually end up with equivalent to solving on 0. So the answer, of course, is not always, because this problem is NP-hard, this is not. And but you can do simulations. The encouraging news is that there is actually a region that if you do the convex optimization, actually you have high probability of success. Right? Precisely when the rank is low enough as a fraction of the total dimension, and the corruption is actually the corruption is actually a small fraction of the entries. So and also you can argue this is also a region we actually care in practice. Right? The data is not totally too corrupted, and also do have low rank that has good structures. Also, if you know which entries are corrupted, and this becomes a matrix completion problem, and then you have a larger range of a working range. So actually, then you can prove that actually under fairly broad conditions that when the rank is bounded from above by almost proportional to the dimension, and the error can be a constant fraction of the entries, and actually you can solve convex optimization indeed give you one truth. This is sort of one of the first results for this problem. And the interesting thing that you can say that the convex optimization has a long adaptive weight factor. But you can solve this doesn't really have any free parameter for you to tune the global minima corresponds to the ground truth. And also you can combine with matrix completion if you have incomplete measurements. And you can see, let's say 10% of the measure, you still can solve the convex optimization giving you the correct solution. And also if you allow to tune the lambda, it actually turns out under the same conditions, if the error has random sign, the fractional error you can corrupt, actually asymptotic approach to 100%. So it actually has this dense error correction phenomenon. Also, you can combine with dense noise. And then in this case, you can stable estimate rather than precise recovery. So I think probably Martin will also talk about what is the statistical implication for some of these algorithms. So there has been, but one thing that there has been a lot of theoretical progress in a few years, right? Many smart people really has done a lot of contribution to this problem, and matrix completion and recovery, including the algorithm and everything, right? But theory is theory. So if we cannot compute this thing at a very, very large scale, very efficiently, then will be useless to a practitioner like me, right? So for example, this problem is actually not that easy. Even for the convex optimization. Right? If you have a 1,000 by 1,000 matrix, in fact, you have to solve a convex optimization with 2 million unknowns. Right? That is very, very daunting if you use traditional material points or traditional convex optimization techniques. So this Turns out in the past few years, there's been a lot of development in the fast efficient algorithm. Probably Mark can also talk more about it. So you can actually solve this kind of problem with unprecedented scale and speed. This is one representative example of algorithm. Just basically this augmented algorithm multiplier, and you solve this in an alternating fashion. And the 3 steps, one step is just do a singular value shrinkage, another one is doing the entry-wise shrinkage. And you iterate, which guarantee to converge to the one, and so on. And as you can see, really during a very, very short amount of time, the speed up by several magnitude. And you actually can compute several thousand by thousand matrix almost in fraction of seconds, several seconds. Probably this is even old. I mean, this is old. By now, there's already probably much faster algorithm by now. So this is nice, meaning that if I have a low-rank matrix with some error, corruption, I can actually recover it under fairly broad conditions, right? So, well, I mean, hence that you can see that in computer vision, we deal with this kind of images, right? We try to recognize barcode, this is wall lens, capture a lot of imagination, and the Google goggle, try to recognize buildings from a picture on mobile devices, right? So they all, you can think about it, they all have very good structure, right? Text and the building facade and also barcode all have very, very good structure. But the practice is that you may take a picture from that arbitrary angle, right? And you have to deal with images like this, right? So even the structure you're looking at actually can be deformed. Right? There's a perspective or even nonlinear deformation to what you do. You can apply RPCA to that, but you'll still get garbage. So the problem is like this, right? So you don't even see the frontal view or corrupted view. You see actually, let's say, a rotated version. For human eyes, we have actually no problem to decipher this image, right? We immediately know this is rotated, corrupted one with a fraction of seconds. But why a computer to do this is very, very difficult, at least up to this work. Right? So now if you look at what's the difference between the red window, the initial window, it's a very bad matrix because it's rotated, right? It's supposed to have a very good structure and with some corruption, but if this is a rotated version, but if you look at the matrix, it's actually the rank is very high. And the columns are not very correlated. But once you can adjust this window, let's say to the green window, then you treat that as a matrix. That can be precisely decomposed as a low-rank plus sparse structure. So now you have to solve a slightly more complicated problem. You don't know the deformation anymore. You have to estimate some kind of parametric deformation of the domain before you get to see the low-rank plus sparse structure. Right? But the good thing is that you can use the low-rank sparse as a goal to achieve, to help you to look for the deformation. Imagine you just try to compress the data as much as you can. Right? The low-rank and sparse are both highly compressible. So hence, what you do, you look for deformation such that you can further compress data better and better. And of course, this has become a nonlinear problem, right? So if you minimize the low-rank plus sparse subject to this constraint, it's still a nonlinear problem. It's not a convex optimization. Well, like any engineer, what we do if we have a nonlinear problem, we linearize it, right? So we can actually try to solve the linearizing problem first. So we can basically solve this incrementally. Every time step, we push this a little bit in a direction, we can actually further compress the data in terms of low-rank plus sparse structure. Right? We do this recursively. Actually, that video shows this process, precise this iteration. Now, if you look at this problem, this is almost like a robust PCA. Right? You have a data matrix. This is a tau. You know tau now. This is a known matrix. You try to decompose into low-rank plus sparse. Plus this Jacobi, you also know, you compute from the matrix, the image. And delta tau, this is a nonlinear. Opposite, this is a linear unknowns, right? You try to compute this term. You can eliminate this by just pre-multiply both sides with a kernel of J, Jacobi images. This actually, you can think about, this is a compressed version of RPCA. Right? You get to see a projection of the low-rank plus sparse matrix. In fact, there's a paper by Richard Meyer talk about this in this NIPS. How to, under what condition you can expect this to work. Actually, we're also still working on this. So now let's just forget about the theory. But one thing I want to say is still, under exact what condition this can actually guarantee to find the correct solution is still quite unknown. It's a rather open problem. So now let's look at what we can use for this for, right? So we'll also show examples with progressively more complicated tau. Here at the top can be an off rotation, offline, projected. We'll see how far we can go. So, in computer vision, the first thing you take a course in computer vision, the first thing you learn is edge detection or corner detection, right? So, if you think about this, it's actually pretty unified. What is edge? Edge is just rank 1 matrix. Right? Corner mostly the rank 2. Symmetry, anything that you have a symmetric pattern, you actually get. So the red window, by the way, the red window is the input of our algorithm. The green window is the output. Right? Converge automatically to that, and then stop. Right? So the license plate, you don't have to recognize license plate from that angle. You can always rectify it. And this is called a shape from texture. Right? There's a lot of work about shape from random texture. Well, I argue actually you can actually get shape, much more accurate shape from structured texture, which has no random texture, right? Like those patterns. And this give you sub-pixel accuracy. And also, by the way, this whole algorithm, remember, we don't do any, there's no feature extraction, no corner, edge, nothing, not even filtering. Right? Just move the pixels around. And it's very holistic. What you see is what you get. Right? So, and you get a very accurate homomorphy, to deformation. And also, anything that has some kind of regularity, this will find it automatically. And then you don't have to do face recognition from that angle. And the video always shows how that will convert. Every frame is a step. And Chinese character, we'll see how far we can go with Chinese character. There are some Chinese here. You can actually imagine. So, how many Chinese characters you can think about? How many Chinese characters are low rank or robust low rank textures? And barcode or text. Well, this actually does this automatically. And if you don't like tilted tower, you can actually always strip by it. Well, later on we'll see we can even flatten that too. Right, we can actually make it flat. Well, it's very robust. I mean, turns out actually this actually once you engineer this, you really have a hard time to fail. I mean, that's the first time in computer vision. If you work in computer vision, you know that things are always a little bit fishy, right? But this is one very few algorithms that really had a hard time to fail. If you fail, actually there's a very good reason.
Well, why do you say that's not features? Because you're entering it into the objective functioning optimization?
Excuse me?
Well, why do you say, one way to do this is you're computing features, but you said that you're not doing features. Is that because you feed it into the objective function?
Yes. We're dealing with basically the observability on the pixel level. Every pixel is a variable, right? So A matrix, E matrix, they're corresponding to what entries of the matrix. So actually you are using all the structures of the pixels together. So they're actually part of the.
But that's not, or you don't think of that as a feature?
Well, you can say pixel are the ultimate features, right? All the information, whatever you extract from the image, you lose information after a picture. So if you look at the computer vision, why, regardless, I work in computer vision all my life, right? All the computer vision, no matter you do reconstruction or recognition, everything starts with local features. Corners, structure from motion like this, you try to recover a 3D model from multiple images, you try to establish correspondence. But the problem with corner is that, it gets occluded. But also there's a lot of features on the same corner, right? Looks exactly the same, it's like the image. When you do correspondence, it's fundamentally ambiguous. But unfortunately, that's where we start. That's why many of vision algorithms are not very robust. Right? Even the first step of camera calibration, if you want to do reconstruction, the first thing you do camera calibration is not automatic. You have to extract corner features, right? So, for example, Microsoft sells a lot of cheap cameras these days, right? And Kinect cameras, but they have to be calibrated. And you know how expensive the calibration rate for calibrating this? Not even very precisely. It costs about a few $1 million just to calibrate, build a rig to calibrate this stuff. Now you probably don't have to. I mean, the traditional, if you do calibration, the toolbox you download from the web, and the most popular one is that you take very many pictures, and you can see there's a really distortion in the camera. What you do, you start clicking. It will guide you through to click in the corners. So this is our method. So you don't have to click anything. Right? So the whole thing is treated as a texture. It will just automatically undo the deformation for you. Once you are done, you are done. You get all the calibration parameter precisely and accurately. Right? So here you just keep clicking. Right? So if you don't have a rig, just go to the bathroom and take some picture of a mosaic, and you still can actually calibrate your camera. More convenient. Also, if you don't care about the intrinsic parameter, if you only have one image, you can at least you can get rid of the radio distortion. So you can have a very bad webcam, make your wife face looks fat. So yeah, that's why women don't like to use a webcam because it looks fat. Also, you can actually do a lot of things now, right? So for example, from all the street view, Google Street View images, I mean, in fact, you get a very, very sharp, precise geometry from images like this, and you can do all kinds of interesting things. The video precisely shows how the algorithm, the optimization path. So actually rectified precisely. Probably nobody has seen, very few seen the Empire State Building from this angle, right? Unless you clean your windows. Right? Yeah, so, and then you actually do a lot of traditional structure from motion become rather simple, at least for this kind of structures. Right? Buildings with multiple facades. As you can see, you to unfold at the intersection, you get a low rank techniques. And also you can actually say you no longer have to do point-wise correspondence. You can do region to region. Then you have a much, much less ambiguity. Right? From a single image, you already get the camera and everything from a single image. That's how we perceive probably the geometry. We don't have to look at individual corners or windows. This is 4 images from a building, you get a precise camera location. And by the way, all this, this compared to traditional method, the advantage is that all the accuracy is suffixal accuracy, right? Because it's completely consistent to the image. Right? Before, if you track corners, you can get a few pixel errors. That gets inherited in all your camera positions and your estimates. And this is also from, if you have A-side building, you only need 8 pictures. Right? You get a very good 3D models. You can actually run the see there's all the reflection, occlusion, so it's actually very, very robust. You can run despite all the work on structure for motion, right? All the public or private systems, highly engineered systems. You can run on this kind of sequence, they all fail miserably. Right? Very simple sequence, fail miserably. There's still a long way to go. And also you have a curved surface. Still, I mean, all change a little bit is the top, it's more complicated, right? Here you have the camera intrinsic parameter rotation translation plus the shape of the curve. So why we are no longer afraid of doing this? Keep in mind, if this is a 100 by 100 window, A and E already 20,000 dimension. You're already doing a pair price to do optimization with 20,000 dimension. Adding another 20 variables is nothing. You don't even see that when it slows down. Right? So basically, if you do the right thing with a high dimensional optimization, the degree of freedom of some of the parameters is actually trivial. In the past, we were very afraid, in the traditional computer vision, we were very much afraid of doing even a computer estimated like 10 or 20 parameters. But now, once you have enough measurements, actually the problem becomes very, very well conditioned. And you can actually build very simple, I'll just skip this very quickly, and you can actually get a very, just to show you the algorithm will just push the matrix, start from a visual to a low-rank texture. And you don't have to do any feature extraction. I mean, you get a 360 panorama to all the. Actually, it works fairly, robustly. You can see this is we tried almost on all landmarks of the regime. It has a curved surface. It doesn't really matter it's occlusion, saturation, taking out the light. As I said, once your engineers did the right thing, it's really had a hard time to fail. We really have to, try very challenging initialization to make it fail. And then you can actually do all kinds of, once you do the computation, you get almost all the local geometry, and you can do all the editing, and adding all those banners. And here you get really sub-pixel accuracy. Your eyes cannot tell the difference. And also all the Chinese characters, they're not low-rank texture, but they're all robustly low-rank textures, turns out. Right? As you can see, this is the rotation of, this is the nuclear norm. It's very sharp. Somehow, I don't know, we don't know why. The nuclear norm is very sensitive to the rotation. The canonical position is very, very sensitive. And you can actually rectify it. It is compared with traditional half transform. And you can actually rectify Chinese character after you rotate them and actually return to the correct position. You can do almost for all Chinese font, popular font, Heiti, Songti, Kai Su, Li Su. Right? And then actually you can enhance OCR. The problem with OCR right now, it only works for frontal images of the text. If you rotate it just by, let's say, 10 degree or 15 degree, drop from high 90s to below 10% resolution. Right, so you can actually do a cell phone, take a picture of some sign, then automatically rectify it, and then you can recognize it. even try English, which has a lot of, let's just show you a, so this is OCR without using the rectification. See, they are already very, very frontal. But see, if you don't rectify them, the traditional OCR doesn't return anything. They don't recognize anything. Right? This is almost like frontal, right? But you rectify, you actually get all the geometry. So this is just to give you an idea that, the perspective distortion actually is a fundamental difficulty for computer vision to do recognition and so on. Right? So hopefully with these techniques, you actually can rectify, can undo the transformation. Undo this transformation, and you can actually make recognition of text, faces, buildings much, much more reliable, and do 3D reconstruction much more easy, without relying on local features, which is traditionally ambiguous and problematic. And also, it's very complementary, right? I'm not saying this replaces features. Of course, you can have features to use it. This gives you additional information. And also, this actually potentially helps a lot with other, image or video enhancement techniques. For example, this is a building facade. If you don't rectify it, you do SVD. You can even take the first 10 terms. The approximation is very, very bad. But if you rectify it, you just only need to take the first 2 or 3. You get a very sharp recovery. We even suggested that when you do image compression, you could gain a lot by rectifying patterns, right? Rectify units. So this is technical messages, right? So there's a lot. Basically, the transform low-rank plus bar structure are really central to a lot of video data. Right? The good news is that now with all the equipped with all the high-dimensional optimization techniques, we can actually compute them at unprecedented speed and scale. We do get those informations now. Actually, they're tremendous. So everywhere you look, you should have information now. You don't have to rely on those individual corners and then try to assemble them later. Right? And this actually hopefully will have a lot of impact or usefulness in processing, to reconstruction. And also, good thing about this is it has a really good holistic nature in it, but you don't really rely on local things, local statistics of images. You deal with regions directly. And I'll just end up with a couple of promotional slides. So to me, why there's a lot of interest to studying this sparse low-rank techniques, and because there's a lot of data and there's a lot of application calls for it. And unfortunately, we start to understand high-dimensional statistics much better now. There's a good mathematical theory. Are exposed to people like us. We can understand the phenomena better. And also, we do have much more efficient algorithm, right? All this convex optimization, random techniques, and actually help us to be able to compute the structures at unprecedented scale and speed. So nothing is really new. We're still facing the same old problem. People tried to do it 200 years ago. But we have new techniques now, right? And the reason why all this L1 gets more and more interested, draw more attention is because, first of all, they actually become more urgent because it actually fits the model of the data better, unlike the traditional L1. And this is actually just one slide summarizes the sort of the parity between sparse recovery and low-rank matrix. And my talk is mostly about this. But you can see that there's a very, very good parity between these two lines of development. Right? People doing compressing and also matrix completion, very much following this line. So maybe I'll just make a joke. But for mathematicians, this is actually a lot of work has been focused on this, right? But for practitioners like us, for engineers, we also have to deal with errors correction because that happens. You don't control the data. These days, most of the data are contaminated. You have to do robust error correction. And very often, especially computer vision or image processing, you have to deal with domain transformation because you don't even get to see the frontal data, the undeformed data in many cases. So you have to solve a much harder problem. And subsequently, of course, they actually gave new problems for you to study. For example, one of the problems is how to solve robust PCA in the compressed form, not the straightforward form. And of course, we see that in math we had this saying that if an idea works once, it's a trick. If it works twice, become a method, right? So suggesting, there's a sparse recovery and low-rank recovery. We have very, very powerful tools. What about other structures? There must be other family of structures, combinatorial structure problems we can solve with similar techniques. So people are starting to investigate in that now. There's some recent paper by Candice and Richard has suggesting there's, I think probably also follow work like the Martin. If you have for large family of norms with good structure, separable structure, for example, actually you can expect the convex optimization to work very well and very efficiently and statistically consistently. Right? So So that's very exciting. We'll see, as practitioners, we'll see what kind of practical problems we can use them to solve in the future. So this is, if you're interested, there are some papers. It's just actually accepted by IGCV, and there's theories on this Robust PCA. And actually, on this website, you can just Google me, and there's a website for the low-rank matrix. We actually have the code for tilt. If you like, you can download its MATLAB code. You can download and play with yourself. Right? And there's actually a lot of work. People at the MSRA are also trying to speed it up, and with better implementation, let's say random projection, to try to make it much faster. And there's lots of engineering that goes into it, making it more robust and efficient. So this is some of the main collaborators in this work. I'm sorry, it's a 1-hour talk, so I kind of rushed it.
Yeah, we have time for some questions though.
So I have a question on the algorithm. So how do you initialize tau1 and then you keep updating tau k? So how do you do that?
Tau just identity. Tau again just identity.
The rotation. So
well, just everything just start from 0, and we just do incrementally.
How do you do that? How do you update tau?
No, tau just you solve the tau by every step you solve convex optimization, right?
Yeah.
And that gives you a data tau. That gives you the data tau that you update.
I see.
So you solve that iteratively. Here. So you say here, there's a delta tau. That's a linear term, right? So you can get it from solving this convex optimization. This convex gives you A, is updated to A, E, and delta tau. Then you update tau k plus delta tau. Just iterate.
Do you optimize the scale? I guess if the transformation reduces to 1%,
great question.
it's 0.
Yeah, great question. So actually, in this case, there's an additional constraint. We'll actually maintain the window have the same error. But that's a nonlinear constraint, but which you can again just linearize it. So, in a way, I don't know if you are familiar with SIFT, right? So the configuration you try to do scale invariant. The SIFT feature actually does fix the location and also the scale, right? But if you think about tilt, that's exactly the opposite. Because the rank is invariant when you change the room in, room out. And also if you shift it, right? If you have a symmetric pattern, if you shift the window, you get the same rank. So this one does not. In the algorithm, we actually fixed one of the point and fixed the scale. So some of these two just do completely complementary to each other. But it corrects all the other deformation. The only thing it doesn't correct is the location, translation, and the scale. So it's very interesting.
Did you try it on the other image, like trees or nature animation?
Well, you have to have structures, right? So, yeah, I don't know. I mean, natural images. Here, we're trying to make a difference between low-rank texture and random texture. There's a lot of study in computer vision. In the beginning, emphasized texture has to be random or stochastically homogeneous or stochastically variable. But here, I want to emphasize this kind of technique is designed for structured texture. If you have structure, it works much better in terms of recovering the shape, recovering the structure, the geometry. That's the difference, actually, very, very big difference.
Any more questions? Or? All right, let's thank the speaker.